Good afternoon, everyone. Let's get started. Today, we are going to talk about recursion. And these are what we are going to cover today. First, we are going to talk about what recursive functions are. And then we will cover a special type of recursion called mutual recursion. And we will compare recursion against iteration. And then we'll see another example of a special type of recursion called tree recursion. And then I will show you some examples and then summarize this lecture to conclude. All right, firstly, recursive functions. So what are recursive functions? In general, recursion means to define something in terms of itself. So this is an example. When we define a tree, we define tree in this way. A tree consists of a root node, which is connected to the roots of 0 or more trees. So when we define tree, we define tree by trees. So it is somewhat confusing. Tree looks like this. We will actually learn how to define and implement this tree data structure in the later of this course. But anyway, this is what recursion is in general sense. In computer science, a recursive function is a function that calls itself in the body of that function. So why do we care about recursive functions? Recursive functions aim to solve given problems by splitting the given problem into smaller or easier subproblems. So you might have heard of divide and conquer. So it is one type of divide and conquer. Sometimes these easier subproblems are actually the same problems as the given one, but on smaller inputs. And if this happens, what we can do is, if the small problem or the given problem is small or simple enough, we just solve it directly. This is called base case. Otherwise, if the problem is quite big, we divide the given problem into one or more simpler instances of the same problem. It should be same. And pass the splitted problems to the function itself. And we assume that our function will perfectly manage the smaller problems. So the beauty of recursion is we solve just small problems and let the function handle the rest of it. Let's have a look at an example. So how do we print a number in base 8? So what is this number in base 8? In elementary mathematics, we learned how to do this. Like we write number here and divide by 8 and like 1, 0, 4, blah, blah. And we write the remainder here and we do the same thing again and again. And when we write these remainders, then it's going to be that number in base 8. Right? And when we see what we are doing here, it is quite recursive. We do the same thing again and again. So we can implement this with recursion function. And it is very easy to find the last digit of a number n in base 8. It is simply n%8 because this percent operator gives the remainder. It is a modulo operation. And the remaining digits are then the representation of this one. So when we actually did this, this number is this one. And this remainder is n%8. So when we actually implement this function, it will have a look like this. So when we want to print some number in base 8. If the number is larger than 8, we just pass the larger number to itself by calling print base 8 function again. So we pass the remainder here. And if the number is small enough, less than 8, we just print n. Actually, we don't need this part. Let's see what happens when we actually run this code. So it is the function we defined, and we put this argument at the end of this print, because when we print something, let's wait a second. A new line is added at the end of this string, given string. And after executing this line, and when you execute this one, the results we will print it on the new line. However, when we want to print a number in a consecutive sense, we do not want to insert new lines. So that's why we put this. So the default is going to be like new line, but we put this. And when we print it's going to be like 12 in base 8. And 12 is going to be 14 in base 8. So let's see what happens if we execute these two functions together. There is no new line here, so the results are printed in a row. And if you want to print these two things in a separate line, you need to call print function without any argument. Then it's going to print out the second one in a new line, because this one adds a new line. Okay, so that was printing a number in base 8. All right, and let's see why it works. In this sense, when we are using recursion, we prove the functionality of a recursive function by mathematical induction. And here, let's say k is the number of digits. Okay. In the base case, when k is 1, there is just one digit. That means n is smaller than 8. In such case, when n is smaller than 8, the remainder of n divided by 8 is just the number itself. So we just print n here. So it will work correctly. And let's prove the inductive step. When k is larger than 1, so it has more than 1 digits, we make the inductive assumption that print base 8 works correctly or perfectly for numbers with less than k digits. So this will work for any numbers with k less than k digits, so maximum k minus 1 digits. If you call print base 8, then you recursively call print base this. But this has k minus 1 digits in base 8. So by the inductive assumption, this works correctly. Finally, we print out the last digit, which is correct. according to the base case. So it follows that print base 8 prints n correctly. So this is how we prove a recursive function works correctly. And when we want to implement factorial, we can use this. By the way, is this the right way to implement factorial? Any idea? In fact, when we run this code, it will not terminate because there is no base case. So let's say if we put 10 here, then it's going to be like 10 times factorial 9. And this would be 9 times F8. And this goes on and on and on. So it does not terminate. So this is a common mistake that you do not put base case. So in the beginning of this class, I mentioned that we need to solve the basic problem at least. So we need to solve base case here. And what about this? Is this going to work well? Yeah, Inson and Hagen gave the right answer. This will not work well because we do not put n-1 here. It will not reach the base case. So it will continue on and on. All right. So these two cases are common mistakes when you implement recursive functions. So be careful about that. And another example I would like to give is summing digits without a loop. So for instance, 2022, we add all the digits in this number. So it's going to be 6. And can you implement a function for this named sum digits? I'll give you 1 minute, maybe 1 minute and 30 seconds. And please implement this function on your own and send it to me if you're finished. All right, thank you for sharing your answers. Okay, let's see how we analyze this problem. So the sum of any one digit, a negative number, is that number. So one digit number, we just return that number. This is our base case. And the sum of a number is the sum of the first digits, which is n/10, plus the last digit, which is n%10. So this is going to be like this. So when this is pretty much similar to what Hagen proposed. So when n is smaller than 10, we just return n. Else, we call the same function here with this remainder and sum the last. One thing to note here is you don't actually need to use else statement here. You can just make the code simplify the code like this. Because when if is called, this return will terminate this function. So it does not proceed to the later part of this code. So it is like just else, even though you did not put else. So you can simplify function in this way. All right, that was recursive functions. Is there any question? All right, good. Now, from now on, let's talk about mutual recursion. Mutual recursion is, as the name suggests, it's a procedure that is divided among two functions, and these two functions call each other. So this is what mutual recursion is about. An example is a number is even if it is one more than an odd number, and a number is odd if it is one more than an even number, and 0 is even. So we can define is even and is odd function in this way. So if n is 0, then is even is true, and if n is 0, is odd is false. And we can call this is odd rather than calling itself. And this is even is called inside is odd. So this is an example of mutual recursion. It's pretty simple, right? And I would like to give an example. The LON algorithm is used to verify that a credit card number is valid or not. So from the algorithm goes like this. From the rightmost digit, so we firstly given a credit card number like this. And from the rightmost digit, from here, we move left and double the value of every second digit. So this. And if this product of a number is greater than 9, like when it's 18, then sum the digits of that product. So it's going to be 9. So it's going to be 0, 7, 8, like this. And take the sum of all digits. And that's what the LON algorithm is about. Can you guys evaluate the LON value of this credit card number? I'll give you 30 seconds. And please evaluate it on your own. Okay, thank you for sharing your answer. Let's see how we evaluate the loan value of this credit card number. So we start from here, and 3 is going to be 3, and 4 is going to be doubled, so it's going to be 8, 7, and this is 16, but it's over 9, so we add each number here, and it's going to be 7, and 3 becomes just 3, and this will become 2. And we add all these numbers, 2, 3, 7, 7, 8, 3, and it's going to be 30. All right. And if the loan sum of a valid credit card number, actually the loan sum of a valid credit card number is a multiple of 10, like this. So this is a valid credit card number. And can you implement the loan algorithm? Think about it for like 30 seconds. We are going to use mutual recursion, and the sum digit function we implemented in the previous slide. How can you actually implement this algorithm? All right, let's see how we can implement this. Because we have different behaviors for every like even positioned number. So we are going to use two functions. Firstly, if n is less than 10, we just return 10. Oh, Hagen, thank you for sharing your answer. So when n is less than 10, we just return n, and we divide these two numbers. So we start from here, and if it is smaller than 10, we just return this value. And if it does have like these parts, we divide these two parts, and this last sum will be just added here. And this part will go to loan sum double function, which will receive 13783. And this will double the last digit like this. And if it is over 9, it will sum digits like this. So it will evaluate the loan digit of the last bit by doubling it. And it is added at the end like this. And these numbers is going back to the loan sum function here, and it goes this. So they call each other like this. So this is one way of implementing loan sum algorithm. And you can also implement this without using this mutual recursion. But anyway, this is how you implement loan sum algorithm using mutual recursion. So is everything clear? So this is to implement two different behaviors. Like for these numbers, okay, thank you for your answer. These numbers are to double the digits. All right. Next, we are going to talk about recursion and iteration together. So when we implemented factorial, it was implemented in this way. However, we can also implement factorial using a loop. So what is the difference? Mathematically, recursion is represented as a recurrence relation. In Korean, it's called 점화식. On the other hand, iteration is represented mathematically this way. And another difference is recursion uses less number of names. So it uses just factorial and n, that's all. However, iteration defines more variables. So here we use total and k. So these two behaviors are pretty much the same. And one different thing is recursion calls functions for multiple times, while iteration does not involve function calls. And because iteration is a special case of recursion, you can convert recursion to iteration and iteration to recursion. Can you convert the following recursive function into iterative function? I'll give you 1 minute to try to convert this function into an iterative one. Okay, thank you for sharing your answer. Harim sent the right answer. And one example of implementing is like this. So we define a variable like this and accumulate the result here. And we can return or print the results like this. So the way to convert a recursive function into an iterative one is what state must be maintained. So here we need to maintain the sum of digits. All right, and we can also convert iteration to recursion like this. So it is simple. So in this case, so thank you for sharing your answer. In this case, we can just pass these variables as arguments to the function call like this. So this is how we convert iteration to recursion and recursion to iteration. All right, next we are going to talk about tree recursion. Here we are going to have a look at Fibonacci numbers. The definition of Fibonacci numbers is this. So the first number is 0 and the second number is 1. And the third one is sum of these two. So it's going to be 1. And the fourth one is the sum of these two. And it's going 2, 3, 5, 8, 13, like this. So this is what Fibonacci numbers are. And it is very easy to implement these Fibonacci numbers. So we are going to implement this Fibonacci number this way. And there is one problem actually, and let's see what that problem is by running the code. Okay, here we are going to call Fibonacci numbers. So this is the function we defined. And we're going to see how fast we can print out Fibonacci numbers. So let's see what happens. So it is pretty fast in the beginning, but as it goes on and on, it takes more and more time. Like it takes more than 10 seconds for each call. And after 35, it is very, very slow. Let's stop. Okay, this is very slow. So our implementation becomes very slow when n is larger than 38, because what we do is calling the same function again and again, like this. In fact, when we are computing Fibonacci 40, Fibonacci number 41 minus k is computed Fibonacci number k times. So this one, Fibonacci 37 is here and here and here. 36 is here and here and a lot. And it's going to be like Fibonacci again and again. So there are so many redundant computations. And the lesson here is blindly applying recursion is not always appropriate. And how can you resolve this redundancy in computation? Can you come up with any idea how to resolve this redundancy? All right, Hung-chan gave this suggestion that we can save the result rather than computing the same result again and again. Inger and Jimin also gave the similar answers. Yes, that is true. We can just save the results in this list rather than computing it again and again. Or another way to compute Fibonacci is using this function. And let's see how fast it can work. So when we save the results in a list like this, so it takes just a second to compute all the results. All right. So the lesson here is do not blindly apply recursion. Okay, that's the lesson here. All right, let's have a look at some other examples. In this section, we're going to have a look at the Tower of Hanoi. So it's the description of Tower of Hanoi. So I guess everyone knows what the Tower of Hanoi is. So we want to move these disks into another pole. So this is a source pole, and this is a spare pole, and this is the destination pole. And the rule is you cannot put a smaller disk, you cannot put a larger disk on the top of a smaller one. So you cannot put like this. So how can you actually move all these disks into this destination pole? So that is the problem of the Tower of Hanoi. How can you implement a function that prints out each step of moving disks? So for example, move disk 1 from pole A to C, and then move disk 2 from pole A to B, like this. So how can you implement a function that prints out each step of moving disks? And to solve this problem, we need to think about how do we divide the given big problem into smaller ones. So here is one suggestion. Rather than thinking about all these disks, we only think about, we divide n and n minus 1 poles. So first, this is source. This is spare and destination poles. First, we move n minus 1 poles to this spare pole, and then move the end pole to the destination pole, and then again move n minus 1 poles from spare to destination. It's pretty simple to think about it in a recursive way. And how can you actually implement this function? So this is one way to implement this function. So we need to give 3 pole positions, like source, destination, and spare. And if n is just 1, we just move disk 1 from source to destination, because this is the smallest one. It can go anywhere. So we just move this disk from source to destination. Otherwise, if we have n disks, we first move n minus 1 disks to spare pole from source, like this. Okay, and in this case, destination pole is going to be a spare pole. And then we move disk n from source to destination. And then we move back the remaining n minus 1 disks from spare to destination, like this. So this is how we solve the Tower of Hanoi problem with recursion. Okay, is this clear? All right. And another example is climbing stairs. So let's say we are climbing a staircase and it has n steps. And the maximum step you can take each time is m. and how many distinct ways you can climb to the top. So for example, let's say n is 6 and m is 4. This is how you can add numbers to reach 6. So the maximum number you can use is 4. So for instance, you can add 2 and 4 to make 6, or 1, 1, 1, 1, 1 to make 6. And it is quite hard to solve this problem using iteration or other techniques. And can you come up with how you can implement this function, climbing stairs function? But think about it for a moment. All right, I'll give you 30 more seconds. All right, let's see how we can solve this problem. Firstly, we need to decompose this problem. And we can decompose this problem in these two ways. First, we use at least one m, or don't use any m. So in the previous example, these two cases used 4 at least one time, and the rest didn't use for at all. So we can divide this problem into two cases. And when we divide these problems into two cases, we can call climbing stairs n minus n, m and m, and climbing stairs n and m minus 1. Because in this case, we are not using m at all. So the maximum step is going to be m minus 1, like this. And n is not reduced. And in this case, we use just m1 for one time. So n is going to be n minus m, but still, we can use m again. So the maximum step is remain still m, like this. All right. And here are some base cases when n is 0 and n is smaller than 0, and when m equals to 0. These are some base cases. And you can think about what you can return in these base cases. All right. I'll give you another 1 minute to complete the implementation of this climbing stairs function. Think about it for a minute. All right, let's complete the implementation. This is one sample solution. So when n equals to 0, we need to return 1, because think about climbing 4 steps with the maximum step of 4. And if you use the maximum step in the first step, and it's going to be like this function called climbing stairs, and it's going to be climbing stairs 0 and 4. And it is just one way of climbing these 4 steps with one big step. So it should be 1. And when n is smaller than 0, it should return 0. When m equals to 0, there's no way to climb stairs, so it's going to be 0. And when we are using m, it's going to be n minus m and maximum step of m. And without m, it's going to be n and m minus 1. So we return these two sums. So is everything clear? All right. If there is no question, let's move on. All right. Before we summarize today's lecture, I would like to take a short survey. This is about class feedback. And please do the survey for 2 minutes. It will not take that long. All right. Thank you for sharing your ideas. Let's summarize today's lecture. Today we defined recursive functions and we covered mutual recursion. And we also compared recursion against iteration. And also we saw how we can convert recursion into iteration and iteration into recursion. And we also discussed tree recursion. And we saw some problems with blindly adapting recursion. And we also saw some examples of recursion. That's all for today. If you have any questions, you can leave, or otherwise you can leave the chat. You can leave now. Thank you for your attention.
감사합니다.
네.
Thank